In this lecture, we're going to take a look at the process of creating an SN diagram for springs to consider springs undergoing fatigue stresses. So to do that, we're going to illustrate this with a problem. So we're going to create an SN curve for a peened A228 wire for a spring with a diameter of 0.207 inches. The first thing we're going to do is find out whether this wire can be made. So we're going to go to the table and make sure that 0.207 is something that A228 comes in, and it does. That is a default material for A228. So that checks out. Now typically when we create an SN curve, what we do is first find the ultimate strength, then find an uncorrected endurance strength, calculate knockoffs that are specific for our problem. That gives us a corrected endurance strength. Then we find the strength at 1,000 cycles, what we call SM. And then we use exponential fitting to find A and B to create an equation that gives us a strength at any number of cycles. So if we know the number of cycles, we can get how strong the material will be at that point. And then finally, we'll use the modified Goodman diagram to find a relationship between our stresses, alternating and mean stresses, and our strengths, ultimate and fatigue strength, and calculate a factor of safety. One of the major differences with springs is that the fatigue experiments were done with repeated stress, as opposed to the fully reversed stress that we're used to seeing for fatigue calculations. So that means that our numbers that we're getting are from a combination of both mean and alternating stress, whereas the fully reversed stress was alternating stress alone. Secondly, the experiments were done by creating springs and testing actual springs, which means that failure was found because of shear loading, not because of tensile loading. And thirdly, we're going to see that the curve is no longer best expressed as a simple exponential curve. It's going to have several regions. Now to show you what I mean by that, let me show you some data here. This is A228 music wire unpeened. There's one exponential region in one location, and then there's another exponential region, and then there's a third. So we're seeing several different regions. So our constants, A and B, for the equation S is equal A n to the B, is going to be changing depending on the number of cycles. The other thing that this table shows us is that there is a major difference between peened and unpeened materials. The process of peening is work hardening the surface, typically with metal balls that are shot at the material, and it makes little dents or peens in the material, and that actually work hardens the outside edge. And by doing that, we increase its fatigue strength. So we have one strength for 10 to the 5th, another strength for 10 to the 6th, and a third for 10 to the 7th. And these percentages of ultimate strength are something that are calculated at the beginning. So rather than getting a single endurance strength, what we're going to get is multiple fatigue strengths at different cycles. So how is that going to change? Instead of the typical creation, we're still going to find ultimate tensile strength, but now we're going to find, instead of just one uncorrected endurance strength, now we're going to find 4 values. 3 of them are fatigue strengths, and one of them is the endurance strength. And I have this W to represent wire. So this is the strength of the wire. We still have knockoffs to find. And then we find our actual values. We still have a material strength that's related to 1,000 cycles. And this is going to be a shear strength now. And so we're going to have multiple A and B's, and that's going to give us multiple equations that will be piecewise continuous. So in this example, using music wire, we'll pull our values from the table using a value for a coefficient of A and B, and we'll calculate our ultimate tensile strength to be about 239 kpsi. Now that we have our ultimate strength, we're going to go to table 14.9, and this spring, it has been peened, so it's increasing the hardness and strength, and so we're going to use these values, 42, 39, and 36% of the ultimate tensile strength. And so we're going to get 3 values here. We'll get our fatigue of the wire at 10,000 cycles, at 1,000,000 cycles, and at 10 million cycles. Now, we don't actually know what the endurance strength is yet. We'll see how that plays in a little bit later. The only knockoffs we need to consider are temperature, reliability, and corrosion, and in this semester I won't take corrosion into account. And all the other factors, size and loading, all of that are included in the experiments, so those C values do not need to be calculated. Okay, so for this problem, we're going to let SEW prime be equal to SEW, which is 67.5 kpsi. What that means is that we're taking all of these values to be 1. Our C temperature will be equal to 1, etc. Finding things in tensile diagram, normally SM would be 90% of the ultimate strength. So in torsional diagrams, the SM shear will be 90% of the ultimate shear strength, and the ultimate shear strength is about 2/3 of the ultimate tensile strength. So that gives us that the strength of 1,000 cycles in shear is about 60% of our ultimate tensile strength. So what we now know are the crossing points. We know up here, this is 60% of the ultimate tensile strength, and then moving down the list, these are the 3 that we calculated, and this one we were given. And what we need to find next is when these number of cycles will happen. I'll go through that in just a minute. So we have this equation that we've already used some this semester, and the equation looked like if I know 2 knowns, a known strength at a known number of cycles, and another known strength at another known number of cycles, then I can calculate the constants A and B from that. So this is our generic equation that if I have 2 known strengths and 2 known cycles, we can get first the exponential term B and then the multiplicative term A. So for in between 1,000 and 10,000, what we're going to use is SMS as one value and 10 to the third. And for our other value, we'll have SFW at 10 to the fifth, and that'll be calculated again at 10 to the fifth cycles. So these will be our 2 governing equations for the first portion of the curve. We can solve for a particular, I'm calling it A1 and B1. Likewise, if I look at between 10,000 and 1,000,000 cycles, now I'm going to use the strength at 10 to the fifth, and there is the log of 10,000 is 5, and here we have 10 to the sixth, the log of 1,000,000 is 6, and so we get now an A2 and a B2 terms. Continuing on, we can do the same thing for 10 to the seventh. And the only other thing, we already know what the endurance strength is, so we need to find out where it starts. So what we're going to do is we're going to continue using this A3 and B3, rearrange this equation here, and solve for the number of cycles when the strength will be equal to the endurance strength of the wire. So plugging all that in, we'll have 1, 2, 3, 4 different values that we can calculate. Again, this one has already been given. For this one, we had to find the crossing point. The 1.01 times 10 to the 10th is where it's going to cross. So instead of at 1,000,000 cycles, we don't reach an endurance strength until we get to 10 to the 10th number of cycles. Now I'm finally ready to plot that graph, and so this is showing the graph plotted in its entirety.